So we're going to start projectile motion soon. And before we do that, we need to talk about vectors in 2 and 3 dimensions. So I'm going to talk about vector addition today. And that's kind of the number one thing I'm going to talk about before we get into projectile motion. There in this chapter, in chapter 3, there is also a section on vector multiplication. And we are going to get into that when we actually need to use it, because I think it makes more sense when it's in context. If I just tell you about the dot product and the cross product, it's confusing. So we're gonna cross that bridge when we come to it. So let's talk about vector addition. Vector addition, basically when we add vectors together, we use what we call the tip to tail method, which means that the tail of the second vector goes on, like, you match it up to the tip of the first vector, and you'll see what I mean in these pictures. So we have vector A plus vector B. All I'm going to do is I'm going to add the tail of vector B to the tip of vector A, and then we can get our resultant vector. So here's vector A again, here's vector B, and then our resultant vector will be drawn from the origin of the first vector to the end of the last vector, which is B in this case. So there is my resultant vector in pink there, A plus B. Now here's some examples of what's happening. So you can do it with 2 vectors like I just did, or you can do it with multiple vectors, but you do have to follow the tip to tail rule. So you can see that here with our 4 vectors, we have our first vector A, the tail of the next vector is added to the tip of the first vector, the tail of the next vector is added to the tip of that vector, and so on and so forth. And then our resultant vector goes from the origin of the first vector to the end of the last vector. So vectors obey a couple of laws, and the first one is the commutative law of addition, which just means that the order in which vectors are added doesn't affect the resultant vector. So if I add A plus B or B plus A, we'll get the same resultant vector here, just meaning you have the first vector and then the second vector, the tail of that one goes on the tip of the first one. So if you flip the order of that, you still get the same resultant vector, meaning the same magnitude of the vector and the same direction of that vector. The associative law is another law that vectors obey, which basically says that when there are more than 2 vectors, we can group them together in any order as we add them, and you still get the same resultant vector, all right? So an example of this would be like if we have 3 vectors, A, B, and C, if we add A and B together first and then add C, it doesn't matter. You'll still get the same resultant vector than if you added B and C together first and then added A. So here's an example of that. Here we added B and C together first and then added that to A, and you still get the same vector as you would have if you added A and B together first and then added C. That's an associative law of vector addition. Now, when we subtract vectors, all we're doing is we're adding a negative vector. So remember, when we have a sign on a quantity that's a vector quantity, such as velocity or acceleration or displacement, the sign just gives the direction. So if we have a negative vector, any type of negative vector, all it is the opposite of the positive vector because it's just giving the direction. So we have here, if I have vector B right here, and I want to subtract vector B, all I do is flip it 180 degrees and then add it to vector A, which makes total sense, right? It's mathematical, makes sense. Now, vector components, this is a very important part of vectors because we will be doing this a lot, especially with projectile motion. So when you see something like this, the football is kicked at 5 meters per second at an angle of 20 degrees to the horizontal, the first thing you do is you break that velocity vector down into its x and y components. The reason for that is because we have to take the x direction and the y direction completely separately from one another when we're doing projectile motion problems, okay? So this should be second nature. You got to do it right away. So we know trigonometry, right? Yes, I hope. So I know that if I'm talking about the cosine of this angle, remember SOHCAHTOA, CAH, which means it's the adjacent side over the hypotenuse. So I have V sub x, which is the x component of that vector, over the hypotenuse, which is V. And then if I solve this equation for the x component of that vector, I get V sub x equals equals the velocity in this case. That's what really we're solving for here. Could be any vector though. The magnitude of the velocity vector times the cosine of the angle. If we want to use the sine, we know that SOH, S-O-H, it's opposite over hypotenuse. So we end up getting the y component of that vector over the hypotenuse, or the actual magnitude of the vector. And then again, solving for that y component of the vector, we get v, the vector magnitude, times the sine of the angle. If we have two of those components and we want the third, we can use Pythagorean theorem. We just get v sub x squared plus v sub y squared equals v squared, which is just a squared plus b squared equals c squared. Now, something that I want to talk about before we do a little mini example in this first lecture is just cardinal directions. Now, everyone knows northeast, southwest. Never eat sour worms, I think is how I always say it. I've heard never eat soggy waffles. However you remember it, it's totally fine. We're doing that clockwise, right? Now, in physics problems, and I have one next that you can kind of see that happening, sometimes they say, oh, this plane is flying 30 degrees south of west, or something like that. And it confuses students a lot. So what I want you to try to remember is when they say blank of blank, right? You can kind of see it happening here. If I'm saying south of west, I start at the west because it's south of that. All right, start at west and then go south of that. If I say north of east, I start at east and then I go north because I'm north of east. If I say east of south, I start at south and then go east. And you'll see what I mean in the next one. But basically, you start at the second one and then go whatever direction it tells you to go first, because you're that direction of the second. I just made that much more confusing than it actually is. But here are your cardinal directions, okay? And I have an example next of how you would actually use that, okay? So here's an example. We have a small airplane leaves an airport on an overcast day and is later sighted 215 kilometers away in a direction making an angle of 22 degrees east of due north. Here's our example of that cardinal direction thing. How far east and north is the plane from the airport when sighted? So here is your here's your magnitude, right, of your displacement vector. I'm also going to label it with the actual magnitude of the vector. And then I've also drawn it in the direction that I want to go. So here is my north direction, and I'm 22 degrees east of north. All right, so that's how you're going to use stuff like that, those cardinal directions. Now, I want to know how far east and how far north the airplane is from the airport when sighted. So all I want to do is find those components of that displacement, the x and the y component. I'm going to call the east vector, which is horizontal, I'm going to call that x, and I'm going to call the north vector, which is vertical, y, just to make it a little bit easier. So let's find east first. Now, I know that that east vector is opposite that angle. So since it's opposite, I'm going to use the sine. So I say the sine of 22 degrees is equal to x, which I'm substituting for the east vector because it is horizontal, divided by 215 kilometers because it's opposite over hypotenuse, right? Opposite over hypotenuse. Okay, next I'm going to multiply both sides by 215 to get rid of it on the denominator on the right-hand side. So I end up getting x is equal to 215 times the sine of 22. Make sure your calculator is in degrees for this. This is 22 degrees. We'll talk about radians later and confuse you guys a lot. It's great. Just kidding. So we solve using our calculator and we get 80.54 kilometers. Now for the north vector, this vector is adjacent to this angle right here. So because it's adjacent, we're going to use cosine. So we get cosine of 22 is equal to adjacent over hypotenuse. So x, I put x again, I meant to put y, I'm sorry, but this is what we're solving for, the north vector. So we get x over 215 kilometers. Solving for our north vector, we end up getting 215 kilometers times the cosine of 22. I just multiplied both sides by 215 kilometers to get rid of it on the denominator on the right-hand side of that first equation. And then plugging it into our calculator, we get our north vector is 199.34 kilometers. So if we get the components of the vector, we can also reconstruct the original vector from the components. All you do is arrange them tip to tail like this. So here's our x component, here's our y component, and then you use Pythagorean theorem, and then you can use the inverse tangent to find that angle if you need to for some reason. So just remember all your trigonometry. You are going to need it when we're talking about vector addition and when we're using, multiple dimensions and stuff like that. All right, let's talk a little bit about unit vectors. Now, most of that was probably review. Unit vectors are probably new for most of you. I'm not sure if you guys use unit vectors in pre-calc or not. But basically what unit vectors are, it's just another notation for vectors. So the notation that we were just using with the angle and the magnitude, it's called magnitude angle notation. This is unit vector notation. All they do is they just give you direction. Okay, so the unit vector, which we call I hat, j hat, and k hat, let's see the little hats that they have on their little heads. You see that? They just are a magnitude of 1 with no unit, meaning when you write that down, all you're doing is you're giving the direction, okay? Just gives direction. So the unit vector I hat points in the positive x direction, j hat points in the positive y direction, and k hat points in the positive z direction. So any vector can be expressed in terms of its components as the vector A is equal to the x component of A I hat plus the y component of A j hat plus the z component of A k hat. All right, so it's literally just saying like these will usually be numbers, all right, this ax, ay, az, but it's saying like I say you had 50 I hat plus 40 j hat plus 30 k hat. All it's saying is that 50 is in the x direction, positive x direction, that 40 is in the positive y direction, and that, I forget what I said now, 50 is in the positive z direction. So it's just giving you the directions of the components of that vector. It seems very confusing at first, but it is really not that confusing. It's just another notation. So here's all our different notations here. Our x and y components using the magnitude and angle. Here's our Pythagorean theorem. Here's how we can find the angle if we have the x and y components. And then here is our unit vector notation. All right, last but not least, I want to talk about the steps for vector addition. So number one, we want to select a coordinate system. Our coordinate system is usually just x and y. Sometimes we have, of course, like north, south, east, west, but I usually just call x horizontal and y vertical. Then we want to draw the vectors. Then we want to resolve the vectors into their scalar components. So all I mean for scalar components is just finding the x and y components. Then we want to combine the scalar components axis by axis to get the components of the resultant vector. And what I mean by this, before I go on to the next point, is you just combine all the x's together and you combine all the y's together. All right, that's it. And then you have all your x's, all your y's, which is going to be your resultant vectors, x's and y's. All right. Then we're going to combine the components of the resultant vector to get the resultant vector itself, probably using Pythagorean theorem. There we go. And then you're going to use a suitable trig function to find the angle with respect to the x-axis. Most of the time, they will ask you for the angle with respect to the x-axis. All right. Sometimes they might not, but most of the time we're looking for the angle with respect to the x-axis. And then you can write that resultant vector in either unit vector notation or magnitude angle notation. If they don't specify, then either way works, okay? Sometimes in the book they will say in unit vector notation, blah, 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 blah. But if they don't specify, either way